Have you ever wondered how a chip is made, or what the inside of one looks like? Well, in this video, we'll take a look inside a modern re-implementation of the Manchester Baby that's made using the open source Skywater 130nm process. The source code for this, and the instructions to build the design are available on GitHub. So we begin with the base, a silicon wafer that has been treated with a p-type dopant to introduce holes, or the lack of electrons in the material. After which, n-type wells are created using an n-type dopant with an ion implantation device, which accelerates and slams the atoms of the n-type dopant into the substrate. This creates a region which contains more electrons than normal. Variations of p and n-type diffusions are made in order to form PMOS and NMOS transistors. These are complementary to each other and form the basis of the CMOS chip. Polysilicon gates are formed using chemical vapor deposition techniques using silicon dioxide or silicon nitride. These are actually formed before the diffusion layer and are used as a sort of masking tape to ensure that the dopants land and form the correct areas. At this stage, the transistors should be fully formed on the wafer. In order to connect everything together, titanium nitride is used to form the local interconnects, which effectively expose the inputs and outputs of each cell so that it can be wired together using metal. All the layers and signals are connected and routed using vias and multiple metal layers, stacked on top of each other and insulated using glass. After all the layers have been placed down, the chip is finally ready. We can see the chip more clearly from up here. Note the input and output pins along the top edge. This design contains 800 cells, over 22mm of wire, and uses approximately 50% of the overall space available. If you were to manufacture this as is, you'd actually struggle to interface with it. This is because it's missing something called a pad ring. As the name implies, it's a ring of pads around the perimeter of the core that exposes the tiny fragile pins of the design to something that can be more easily wire bonded to. The reason this design doesn't contain the pad ring is because it's intended to be a part of a much larger chip, a multi-project wafer, that contains many more custom user-submitted designs. If that interests you, and you want to try to make your own chip, then you should check out Tiny Tapeout. As we zoom back into the chip, I'll hide some of the metal layers so that it's easier to see the cell itself. A cell is a pre-designed, pre-characterized, and pre-verified block that performs a specific logic function. Here we have one of the many AND gates in this design, and the particular variant is listed below the title. There can be many variants of a cell, each configured slightly differently for density, speed, available space, and leakage. Overlaid here is the foundry provided diagram, which makes it easier to understand the different components of the cell. Shown on the top and bottom, colored in purple, we have the voltage and ground rails respectively. They are always on the tops and bottoms of cells because this allows for easier placement and routing. As this is an AND gate, we have our inputs A and B, along with our output X on this long bar on the left of the cell. PMOS transistors are where red overlaps with orange, and NMOS transistors are where red overlaps with green. Orange is P diffusion, green is N-well, and red is the polysilicon gate of the transistor. The top half of the cell here forms the pull-up network, and the bottom half forms the pull-down network. This specific arrangement helps to provide strong logical ones and zeros, whilst also reducing power consumption. We can count how many transistors this is made up of by simply counting the number of overlaps with the gate-doped areas. In this case, we have 6 transistors. We can also extract the actual transistor schematic by reading the diagram. We know how many transistors there are, and of what type, but we can also see how they're wired together. This is shown by the black boxes with cross-through, which indicates a via connection to the layer below it, and the blue polygons, which indicate the local interconnect, which is basically a wire. The first transistor is PMOS, with its source connected to V power. The same is repeated for transistor 3, as their drains, or outputs, are connected together. This output is also driven by transistor 2, which is an NMOS transistor. The gate of transistors 1 and 2 are driven by the same input A. The source of transistor 2 is the drain of transistor 4, so they are drawn as one on top of the other. The source of transistor 4 is V ground. The gate of transistors 3 and 4 are driven by the same input B. These transistors form a NAND gate, the output of which is the wire being driven by both transistor networks. This is connected to the gate of transistors 5 and 6, which form a NOT gate. This inverts the output of the NAND gate, forming the final AND gate. And we can finally take the output X. The exclusive OR gate, which outputs a 1 if the inputs are mismatched, takes 10 transistors to make. It has inputs A and B with an output X. Its schematic looks something like so. The delay flip-flop, used to store a single bit, is a considerably larger cell than the others. Its inputs consist of a data input as D, active low reset as reset bar, and a clock signal as CLK. The cell will store the state of D if clock goes high and reset bar is high. This will be output to Q. In contrast to the D flip-flop, the NAND gate only takes 4 transistors. We saw its schematic in the AND gate we first looked at, so the only difference here is that it's missing the NOT gate at the end. The OR gate, outputting a 1 only if one or more inputs are high, is also simpler than the XOR gate we saw earlier. It's made up of only 8 transistors. Open source software and hardware has matured to a point where you, as an individual, are able to get a design manufactured without breaking the bank or without years of experience in hardware design. This wouldn't have been the case 10 years ago. It's a very exciting position to be in, and I recommend checking it out even if you are slightly interested in this stuff. All you need to get started is a free weekend and a simple Wokwi or Logisim project. And if you get stuck, there's a Discord server that you can get some help in. To give you an idea of what can be made, here's a small selection out of the hundreds of users submitted designs, all of which have been manufactured via Tiny Tape-Out. We've got chip tune generators, completely custom CPUs, an oscillator made from skulls, a very precise voltage divider that outputs pi volts, and a GPU that can render a quad with a texture applied to it. So go make something cool, and go show it off to everybody.